the gas from this star, accreting it onto here. Now, remember, I told you stars, they take hydrogen, they take light elements and make heavy elements. If you've got a big ball of gas here, that's basically fuel. So you've got a dying ember here, you throw fuel on it. What happens when you throw fuel on a dying ember? You get an explosion, right? So this gas accretes on here, and eventually there is a thermonuclear runaway. It's just the surface of the white dwarf. The white dwarf is really hard. It doesn't go anywhere when this explosion happens. It's just the surface layers that blow off. And that is what we call a nova. All right, here's the super sciencey part. We're going to talk about what happens in what's called an HR diagram, because astronomers, we love our diagrams. What we're seeing here is a plot of temperature at the surface of the white dwarf. Just ignore this star now. We're just looking at this one. Temperature at the surface, and this is how bright it is. And the units are a little funny here. I'm using units of Kelvin, and it's on a log scale. So this is 10,000 Kelvin. You guys all know Kelvin? Yeah. Probably heard it. The sun is about 6,000 Kelvin. So sun is over here. It's much hotter than the sun. This is a log scale. This is 100,000 Kelvin. This is 1,000,000 Kelvin. This is really screaming hot. This is brightness. It's all again on a log scale. So the sun is 0. This is 10 times as bright as the sun. 100,000, 10,000, 100,000 times as bright as the sun. So a nova starts here, the system before it explodes. When you just have a white dwarf sitting there next to that star, it's down here. Then you start putting that fuel on it. What happens is it gets hotter and hotter and hotter, but it doesn't change in size. It stays the same size, so it creeps up this diagram like this, gets hotter and hotter. Then you get to a point where the fuel ignites, and you start getting thermonuclear burning. And then it really starts heating up, but it doesn't go boom, right? This is something we've learned fairly recently. Like if you talk to many astronomers, they'll say like, oh, right there, boom, it's going to explode. No, it just simmers. It just gets hotter and hotter and hotter, really, really hot. And it gets so hot that it starts emitting actually light in the X-rays. That's how hot it is, incredibly bright. But it's still basically the same size. But it starts putting out so much light, tens of thousands of times as bright as the sun, so much light that the photons, those little, massless particles, they have momentum. They start bumping into the gas and pushing it. So you can actually push something with photons. If you've seen Star Trek, again, there's like a solar sail and you can have a wind and it can push it, right? That's a real thing. You can have light, just photons, shining on something and it'll push it away. So at this point, it's got so bright, it starts pushing the outer layers and they expand. And when you have a hot gas and it expands, it cools down, right? Like you ever take a can of air and spray it, the air comes out cold, right? Because it expands. So the surface layers start expanding, and then there's something interesting happens. All right, this is the hard part. So stay with me here. Remember we talked about those different energy levels in the atoms? Those are the only energy gaps, the only energy levels that it can absorb light at. Now, when it's really, really hot, you're starting at a very high energy level, so there's basically little absorption of light. The light just goes straight through it. When it cools down, you start getting to lower and lower energy levels, and you get to a point where it can start absorbing photons again, right? So what we say is it becomes opaque. It's transparent, and then it becomes opaque. And right about here, suddenly all those photons start pushing on the outside, and this is where the explosion begins. This is where the outer layers of the star blow off, and it gets, in the optical, in our visual light, it gets brighter and brighter and brighter, and then all that gas gets so far out that it starts to thin out and you start to see into deeper and deeper layers. And then you see in those deeper layers, which are hotter, right? And it goes back this way, and then the wind stops, and then it cools down, and then the whole process can repeat again, right? This whole system survives. You think about all that gas exploding, but it's just a tiny bit on the surface of the star. So this star doesn't care, just no problem. The white dwarf doesn't care, so it repeats, and it can repeat every, thousands of years. Some systems repeat every year, but most of them are like thousands or tens of thousands of years. All right, did we make it? Okay. All right, so what can we do with the data we got? Actually, let me go back a second, because I kind of skipped over this. Oops. There we go. here's the data. So we saw this rise. We got to see it blow up in real time. But right here, this is actually where all the interesting stuff happens. So let's zoom in there. Okay, that's this plot here. So this is that big rise going up, and then this is what it did early. So this is the historical light curve from ZTF. So we're looking over 3 years, it stayed this bright. And then right about here, this is a gap in time. Now these are days here. So these are actually just a few hours. A few hours, it went from how bright it had been to, let's see, 100 times as bright just in a few hours. But it did it this way. It slowly rose, and then there's this dramatic tick right here. So what is this transition here? This is the point right here, C, when that atmosphere suddenly becomes opaque and the photons start pushing it apart. That's where the explosion begins, right there. So we caught the explosion right as it was leading up to explosion, then boom, right there. All right. All right. Let's see. I'm debating how much I'm going to push it here. I got a few more like really sciencey stuff, and then I've got like some fun stuff.
How many objects like this are detected?
How many objects? There's only one that we have this great light curve for. There are many nova. Every year there's about 6 nova in our galaxy that are detected. Maybe actually sometimes there's more, but there's like 6 good ones, I guess. But no one's ever got a light curve like this before. This kind of data is very unique. How do we feel? Do we need a break from all the sciencey stuff and want some pretty pictures, or do you want to like really dig deep? Dig deep. All right, good crowd. All right, so the exciting thing that was discovered about nova in the last kind of 10, 15 years is that everything I just told you about how they're powered is insignificant. So if you look at nova, we're talking, let me go back to this diagram here. I said they get really hot. They get so hot they can shine in the X-rays, right? So just to give you temperatures, like visual light's here, and then there's ultraviolet, and then there's X-rays, and then what's over here? Do you guys know what's over here? Gamma rays. That's right. If you get to even crazy high temperatures over here somewhere, you get gamma rays. Now from a nova, they never get that hot, so you don't expect to see any gamma rays, right? So of course, what do we see when we put in our gamma ray telescopes at nova? We see gamma rays. So this was observed with a satellite called Fermi. This is the same nova, B1674 Her, and it started off bright and then faded over about half a day. So where are these X-rays, these gamma rays, where are the gamma rays coming from? This is the dominant source of power in this. These dots, by the way, this is the data I was just showing you. All right, I put it on a different kind of scale. This is on a linear scale instead of a log scale. So it looks a little funny, but you can still see there's the thing, and it goes up and gets brighter. Amateurs took data, and then it faded away. But these 3 purple dots, that's a big mystery. So how do we explain that? Okay, so there's a couple ideas on how you can get gamma rays. We're not going to do it with temperature. We're not going to be able to get the gas hot enough. But what we can do is we can rely on shocks. So if you see gamma rays, you're thinking, I've got shocks. So again, we've got this white dwarf star starts inflating, right? Because it's blowing up, it's getting bigger and bigger. Eventually it gets to a point where there's this point called the L1 point, L2 point. This is where gravity is balanced. So you've got this star here. This is your lightweight donor star. You got your heavy white dwarf here. And if you put something right here in the middle, gravity is going to be balanced. It's not going to want to go either way. But it's unstable. If you put it a little bit this way, it's going to fall here. You put it a little bit that way, it's going to fall this way. All right? So gravity, both of these stars have gravity. They're pulling on stuff. And if you get close enough to one of them, that one's going to win, and gravity's going to take. Just think of like you have a little rock, and you put it right here. You tip it just a little bit this way, it's going to go onto the donor. All right, but the donor is actually already full here. It can't take anything more, so the gas ends up going out to the other side, to the L2 point, and gets squirted out. So here's what happens. You got these 2 stars, they're orbiting around each other, and gas starts spraying out like a nozzle, like on a, think of a garden hose just kind of going around like that. and you start spraying gas as this nova starts to erupt. This is in the slow rising phase, and eventually there's that transition where it starts going fast, right? So you got all this slow moving gas that's slowly going away, and then inside here, boom, you got this fast moving gas which starts shooting out. That can cause a shock. You've got slow moving gas and it gets hit by fast moving gas. You can get shocks, and that's how you can get gamma rays. So just to show you, this is that same kind of spiral, garden hose thing here. This is a side view, just looking down. So you have a torus of gas going around from the garden hose effect, and then boom, the pink is kind of the fast moving gas. It smacks into it, and then we think that's where gamma rays can be made. So that's one idea. Second idea goes back here. Remember, the star is getting bigger here. It's expanding, right? And as the star expands, there's an interesting thing called the escape speed. You guys know what the escape speed is, or escape velocity? That's the velocity you need to get an object for it to leave a body like the Earth, say, and go off into space and never come back, right? If you take, let's see if I can do this. Oh, we got the pressure on. If you take something and throw it up easy, it comes back down to Earth. You throw it up harder, it goes up higher. How fast do I have to throw it so that it never comes back? About 25,000 miles an hour, which I cannot demonstrate. But if you did, it would go off into space and it would never come back to Earth. All right. Now that speed depends on two things that are important: the mass of the Earth, or if you're talking about nova, a white dwarf, and the radius, how far away you are. The farther away you are, the less speed you need to get away and never come back. So as this is expanding and getting bigger and bigger, that escape speed is going down and down and down, and the wind that's being blown off is slower and slower and slower until it turns around and starts going back into the photosphere, and then the velocity increases with time. And so what happens is you have slow moving gas, and then fast moving gas comes and hits it, and then you get shocks. Okay. So which one of these is right for our nova? Well, there's a problem with the first one. The problem, it takes time to make all this. All right? If you're starting to spread out gas here, you need to do this. You need many orbits to spray all that gas out there and make that torus. And when we look at our data, not this data, but this data, this is only a few hours. It's not enough time for it to do that. So what we think is this second model is actually the right one. We think, by looking at our data, that when the star exploded, we had a wind that slowed down over time and then sped up, and that wind made the gamma rays that powered the peak of the nova-like curve. Did we make it? Oh, good. That's a good crowd. So that's my paper. That's fantastic. You guys followed along there. All right. Thank you. All right, you guys have been good, so I promise you we'll just do some fun stuff now. Okay? So first of all, you guys all want to see one of these, right? All right, so I'll tell you where to look. Maybe. There is a star called T Corona Borealis. Coronae Borealis. It's in the constellation Corona Borealis. If you go out tonight, it's up. It's between Hercules, right? There's a trash can on the sky. And there's Bodes, which is the kite on the sky. Right in between those two, there's this little crown. It actually kind of looks like a crown. Right? It's kind of a ring, maybe a tiara, I don't know. But there's this ring of stars here, and you can see it. And if you go off of this star here, go off of Epsilon, right there, you'll probably will see nothing. But keep looking. There has been a nova here before. It's gone off at least twice. That's been recorded. And it's due to go off again. It goes off about every 80 years, 70, 80 years. And there was a prediction that it was actually going to explode last year. It didn't explode last year. We're still waiting, so keep looking up there. And if you see it blow up, let me know. Okay. All right. One more thing. Even more fun here. I am the director of the Mount Laguna Observatory, and I've got all these cameras that I have access to, and I make videos just for fun. So I'm going to invite you guys to go check these out. I actually have two types of videos. One, if you like the sciencey stuff I was just talking about, I can teach you how to be an astronomer. I take my lectures that I give at San Diego State, and I record a version of them, and I post them online. So you can see my actual lecture material online. The other thing is I have these videos, which I'm highlighting here, which are more just for general education, just for fun. Let me show you a couple of these. Have you guys seen this one before? Let me show you this video here. So I took a camera. We have a camera that looks at the site. It doesn't look up. It just looks west, and it takes pictures all the time. And so I just took one at every 24 hours. So this is the sun right there, and then 24 hours later, the sun's in a different position. And so if you just show every day at the same time, this is what the sun does.
Oh, look at that. Oh, that's so cool.
Have you guys seen this video before? Anybody here? No? All right, you got to update your feeds. This is the good stuff. All right, so I have videos like this. If you like that nova we were just talking about and you want to see a video of it, I've got this one here. This one starts with our all-sky camera, and it just zooms in where the nova is about to explode, and then it shows the data from every scope. So this is our all-sky camera. It zooms in right where that nova is going to be. It's a little fuzzy. It'll clear up. There's every scope, and then pink. There's the nova right there. And then the camera didn't work, and then it worked again. You guys saw the video. And then I zoom out to put some perspective on it so you can see where that dot is in the sky. It's right there in the Milky Way. All right, so that's fun. I got one more for you, one last video. Since this is a dark sky event, I did want to highlight that I have a video that is related to dark skies, and I'll just let it play here. So what I did was I took a similar set of cameras. There's cameras at our observatory, and there's another site that has the same cameras. This is on Mount San Miguel, which is east side of San Diego. So if you look west, you can see Escondido, you can see La Mesa, you can see San Diego coming around here. So you can see the city, which is pretty, but also there are stars up there. But you can see they get washed out by the glow, by the light pollution. Right, so what can I do? I can show you now, I'll look south, and I'll show you this and Mount Laguna Observatory at the same time. So this is what light pollution does. This is with no light pollution. So you can see much clearer view there with all the stars. Right. So maybe I'll just stop there. I'll let you guys visit my site. I got a whole bunch of videos if you're interested. And that's what I got today. So thanks for coming. Happy to entertain questions if anybody has any. So maybe I want to let people leave though, because I just talked in a long time. But you have a question here?
Yeah, what's the largest telescope you have?
The largest telescope we have that's operating is a 1 meter telescope. That's the one that I've showed a lot of the data from. We also have a 1.3 meter that's being constructed, but we're having issues with that, so it's not up and running just yet.
Okay, thank you.
But 1 meter means the mirror is 1 meter. It's about this big across. The actual telescope is twice as tall as me. It's a big thing. Is there a question over here? Yes, in the back. The gamma rays from the nova. For this one, they only lasted about 12 hours. It was a pretty short, maybe 18. It was a pretty short duration gamma ray flare.
So they say that when Beetlejuice will explode, it's just throwing like gamma rays. The potential duration for this thing.
Yes. So I showed earlier that sometimes I look at gamma rays events. Let's see if I can go back to that slide. There you go. So I talk mostly about nova, just regular stars with the envelope exploding. There are also supernova, and then there's the gamma ray bursts, which is the more exotic ones. So these can occur when you have a very massive star that collapses and forms a very even more dense object than a white dwarf. You can have a neutron star that forms with huge magnetic fields. So you got the mass of the sun, even more mass than the sun, in a ball smaller than about San Diego. Tiny ball with huge magnetic fields rotating 100 times a second. These are crazy, crazy objects. And with all that going on, you can get powerful jets that shoot out from them. So you get these very powerful magnetic fields. Charged particles go along magnetic field lines and they spin around, they emit light, and that can make what's called a gamma ray burst. You get these very high energy photons. From massive stars, so the question was how long do these last? From this type of gamma rays from a massive star, they last a few seconds. The actual gamma ray pulse is not that long. It could be up to, I think the longest I know of is like an hour or so. There's another type of gamma ray burst. We have two neutron stars that merge. Those are less than 2 seconds. The burst is less than 2 seconds. Yeah. Was there any other questions?
I have some weird question, not really related to your talk.
Weird question, not related to my talk. I'm in thrall. I'm excited. What is it?
Well, I noticed you had the slide with some of the YouTubes you've done.
Yes.
And you've done one on zodiacal light.
Yes.
Why do we care about zodiacal?
Why do we care about zodiacal light?
Dr. Brian May from Queen, he went back after 20-some years, finished his PhD in study of zodiacal light. And what I can't understand is, why is it interesting?
Why is it interesting? So there's two reasons why it's interesting. One, if you're an astronomer, there's three reasons. One, it's actually pretty cool. If you go out and you look at certain times of year, you got to go out in like September and I think April, and you look right before sunrise or right before sunset. It's harder at sunset, but if you go in September, right before sunrise, you'll see this kind of finger of light it shoots up. And this is in the plane of the Earth's orbit, all the planets' basic orbit. So we call this the zodiacal light because the zodiac are the constellations that are in the plane of the solar system. Now, why is this interesting? As an astronomer, if I'm trying to find the faintest, most distant supernova I can find, I don't want to look here because it's too bright. So I want to look over here. So that's my main interest in it. The other thing, though, is why is there light here? What's making that? So if you watch the video, I'll give a spoiler here. It turns out that there's dust in our Milky Way, not our Milky Way, our solar system. There's dust in our solar system that's reflecting sunlight. And the source of that dust is actually Mars. And that's a fairly recent discovery. Mars actually has these dust storms, and that dust sometimes leaves the surface of Mars, and it goes and pollutes the sky. So it's kind of a light pollution thing, but it's more of a natural light pollution.
Okay. Cool. Thank you. That's all.
All right, I think I've used my time, so I'll be around for a little bit if anyone has any other questions, and thanks for showing up.
Thank you so